Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be continuing our study of methods for computing roots of equations by looking at the Newton-Raphson technique. We are in particular looking at solving this cubic equation of state generated for chlorine by the Peng-Robinson equation. And we'll just be looking at one case of this for now. So the Newton-Raphson technique is based on a first-order Taylor series approximation to your function. So if I do that, what you see is you just get the function evaluated at a specific value called x sub I times this change in x times the first derivative of the function evaluated at x sub I plus some higher order terms that we're going to assume, if we're close, are going to be quite small. And so now then, if I just throw out all those extra terms, I end up with this as my expression, where I'm assuming that, that function f of xi plus 1 is supposed to be equal to 0, right? And so I can take this and solve for x of I plus 1. And this gets me an approximation technique. So x sub I, one fixed value, unlike all our other techniques where we've needed two starting points. I need one fixed value minus the function evaluated at that fixed value divided by the slope of the function evaluated at that fixed value. If we were to look at this graphically, then what we see here is we have a function, and we're simply going to choose an x sub I, evaluate the function and its slope. If you take the function and its slope and divide those, that will give us a prediction of what x sub I plus 1 should be, our next guess. And we'll do that again and again, and it will drive us very quickly towards the actual root of the equation. Well, supposedly. Really, this is very logical mathematically, and it converges very rapidly, except for those times when it doesn't. So what can go wrong? Well, if we look at this expression here, it's nice because it only requires knowing one fixed point, but I have to have an analytical expression for my function and its derivative. So I have to be able to take the derivative. And worse than that, the derivative is in the denominator. So the denominator can't be 0. The slope can never be 0. Now, look at this function drawn here. This is an oscillating function, and it has slopes of 0 all over the place, right? We have a slope of 0 here. We have a slope of 0 here. We have a slope of 0 here. And if I don't choose a first guess that's close enough to the answer that I want, it's going to send me bouncing all over the place. So for instance, as shown here, this one sends me to a guess here, but now then, because of this again, 0 slope, it's going to send me over here. And it's just going to bounce me all over the place. So the first guess is going to need to be very close to my starting value if I have division by 0 or other math ugliness that would make this be not analytic at all points. So that's going to be our problem. As far as when to stop, we're going to still be using relative error limits. So this has not changed. So let's look at using this in Excel. So let me minimize this. And I have this now, same problem. Let me scoot on down and let's look at the Newton-Raphson technique. So f of z is this expression over here where it's basically z cubed plus a number times z squared plus another number z plus another number. And the derivative of this is pretty simple, 3z squared plus 2az plus b. And it's unlikely that this is going to be exactly equal to 0. Unlikely, okay? Except for at certain points over here, but we do have a good first guess. So by using our good first guess, I have my starting point. So I want to figure out what my second value is. So I've already figured out f of z. Now I need to know f prime of z. And so that is simply going to be 3 times the z value squared plus 2 times my a value, which I'll pick up over here, times the z value, plus the b value. And I don't need the c. Okay? And again, I'm going to use the F4 key to make those absolute references. And now then I can copy this on down to several new choices. Okay. I don't have a value of z in there, so don't worry about what those numbers are right at the moment. Okay, so I need to put in my new guess. So my new guess is going to be my previous answer minus the derivative from the previous answer divided by minus the function divided by the derivative. Okay, I do have it typed correctly. And so we'll see that this is going to, and I can just copy this formula down. I don't have to do any clever figuring out which is positive or negative. I can look at this to many more sig figs, and you'll see that by the third guess, it had me very close to the right answer. Now, what if I hadn't chosen such a great first guess? What if I had gone with 0.7? And you're going to see that, again, it doesn't take very many steps before it has me to that same correct answer. So the Newton-Raphson is a very powerful technique, but it is prone to problems when you guess poorly. So what if I had guessed 0.1? What does it do then? Well, it managed to jump over to the other side very quickly, and it is going to eventually bring me down to the correct answer. Okay, it got me there. Sometimes that's not so lucky, so I don't even know. I haven't tried this one before. So if I try 0.2, oh yeah, 0.2 is a disaster. It's not getting me there. It's going in between this positive and negative change in slope, and it's just bouncing around and it's lost. So it does depend on a good first guess. But with that good first guess, and it doesn't have to be awesome, it just has to be good, then it converges very rapidly. So this is the Newton-Raphson technique. This is used in many, many problems. You'll have many faculty recommend that you use this one. Again, the conditions being that you have to have a good first guess and you have to have an analytical function with its derivative. So in our next lesson, we're going to be looking at the secant method in Excel, and we will also be doing this in Visual Basic. Thank you very much for your time.